In this video, we're going to show an example where we look into our residuals for a simple linear regression model and we think about the model assumptions. So recall that our simple linear regression model is yi equals beta naught plus beta 1 times x sub I plus some model error term epsilon sub I. Okay? For I equals 1 to n, and in this example, I have 187 observations. All right, so what am I looking at here in this example? I have the country that people live in, and then the average life expectancy in 2010 for the people in those countries, and the average income in 2010 for the people of those countries. So what I'm interested in examining is, does income per person predict life expectancy? So life expectancy is my y, and income per person is my x. Okay, and so let me just make these a little bigger so you can see that, x and y. All right, in our model assumption, in order to run this model, I need the assumption that the expected value of these model error terms equals 0. Okay, and the way I'm going to look into that is I'll need to figure out what my residuals are. I'll plot my residuals versus x, and what I'm hoping to see is that centered on 0, so these residuals, which are e, right? So this is a plot of e versus x, right? I'm hoping to see just like a random scattering. Anything other than a random scattering is potential that the model is incorrectly specified, and this assumption would be incorrect. So for example, if my residuals, instead of being a random scattering, if they have some sort of trend, right? So the next model assumption that we're going to look at and think about is the variance of my model error is constant, right? And the way we'll know that whether or not that's true is the variance of sigma squared. It's constant, homogeneous variance assumption. If we have, the residuals being really close to each other and then they get really big, so like really close and then getting wider and wider, this type of cone shape residuals suggests that the error is not constant. The variability of the error is not constant, right? Rather, it depends on I, which would be a problem, and that'd be something we would have to address. Okay. Another assumption that we're going to talk about in this video is the normality assumption, that our error terms are normal, right? And we'll talk about how to examine that. We'll do that with a histogram of our error terms, and we're hoping to see a normal distribution. And then we will plot our semi-standardized residuals, E, against some Z value, and we're hoping to see like a straight line. So that's a probability plot. Okay, so we'll do a probability plot and we'll do a histogram. All right, so that's the goal for this video. Now, the one assumption that I'm not really talking about in this video is that my error terms are uncorrelated. And this data, a good way to look into that is if there's some sort of time trend. But this data was all collected at the same time. So I can't plot this data versus time, or like the residuals versus time. That's not going to do anything because it's all collected on the same time, 2010. If I had another variable that I thought may make my residuals be correlated, so if my residuals were correlated with, say, eating habits, if you had some sort of marker or data on eating habits, you could potentially examine the residuals versus that other variable and see if there's some sort of correlation. Okay. Let's go ahead and get started by looking at these three. First thing we need to know is what is our residuals. Well, to determine our residuals, we need to know what the estimates of, so remember y hat I equals b0 plus b1 x sub I, right? And a residual is the observed value minus the predicted value, okay? So to figure out what my residuals are, I do need to figure out what these estimates of B0 and B1 are. So to do that, let's go ahead and go up top to data, data analysis, scroll till you see regression, press OK. Y input, highlight my data. So start with your cursor on the label, shift control down to highlight all of your data. Move your cursor to the X range, scroll up, and shift control down. Okay, get all your X range data. Labels means that when I highlighted my data, I included the label. Output on a new workbook. And I'm going to go ahead and click all of these, and we'll have to talk through these, okay? So just press OK. Okay, so I'm going to relabel this. I'm going to call this the toolpack results. Okay, so looking at my toolpack results, I see that my R squared value is 0.35. That means 35% of the variability in life expectancy is being explained by income. That's really a pretty poor R squared value. All right. My p-value, however, is really significant, which suggests that income is a good predictor of life expectancy. So that's an interesting contradiction. Well, remember, these interpretations, they depend on these assumptions. So let's look at our assumptions before we actually start interpreting what each of these, what all this means. Okay, so the first thing I want to do, I'm going to create a new sheet, and I want it to be E versus X. So my residual versus my X value. Go back to data. Let me scroll up, and I want to highlight this, press Control C, and I want to paste it there. Okay. Now, in order to figure out what my residual is, I need to know my predicted value. Predicted value, which is like y hat. Okay. And in order to figure out my predicted value, or y hat, I need this analysis toolpack. I need these coefficients. So I'm going to copy this, press Control C, and I just want to put it somewhere over here. All right. So these are my coefficients. This is B. This first one is B0, and the second one is B1. Right? And y hat is B0 plus B1 times X sub I. Okay? So my predicted value, or y hat, let's write in a formula for this. So equals B0 plus B1 times the X value. Okay? Now G2, which is this blue, I want it to be always there. I don't want it to move. So to lock it there, I use these dollar signs. Now B2, I do want that to move, right? I want it to change. I want to go depending on what observation I'm looking at. Press enter. All right, get your cursor there. Make your cursor look like this black X or cross, and then double click. All right, and it'll automatically fill in that formula. So we see it's using it correctly. So B0 plus B1 times our X value. Okay, and they should all be doing that. All right, so that's my predicted value. So my E, or my residuals, right? My residuals, E, okay, equals my observed value minus my predicted value. Okay, press enter, and then press this and double click. Okay, I like for everything to be formatted the same up top, so let's go ahead and do that. Okay. All right, so good. I have my residuals and I have my X value. I'm ready to do that plot. So let me go up top here and press insert and do this chart. Press scatter. Okay, move it off to the side, and then right click, press select data. Okay, let me move that, and then press add. All right, the name of it, I'm going to go ahead and title it E verse X. The X values, okay. Now make sure you do not click the label. If you do that, it's going to mess this up. So just include the numbers now, okay? So click on your number, and you can click and drag and hold it down. A quicker way is to start at top one, then press Shift, Control, down arrow, and it'll highlight them all together. Okay, Y values, delete what's there. And let me scroll back up. Right, and I want these residuals. So again, don't click up here. Start with your actual number, Shift, Control, down. Okay, and double check. So you see how it says B2? That means it's starting at B2, right? Column B, row 2. And then also C, starting at D2. So that's right here, good. Columns D, row 2. And then going all the way to 188. Good. Press OK. And then press OK. All right, and then this is my plot of my residuals versus income. And of course, you can make this plot look a little nicer by adding, labels. You could label your vertical and horizontal axes. I recommend that you do that. But for right now, I'm just going to leave it like this so we can just look at it. What do we see here? All right. A few things, actually, potentially. You do kind of see the coning, right? And the coning shape, that indicates that there's the potential that this homogeneous variance assumption is not being upheld, right? So the variance of my error terms do not appear to be constant. Right, another thing that you're seeing here is that I do kind of see potentially a relationship between the residuals and X, right? And that's really bad. That means that the model may not be correctly specified. Okay, so this plot here, it looks real bad, right? What we want to see is just a complete random scattering around 0. But that's not what we're seeing here. Okay, so that's pretty interesting. We definitely would have to do something about this, right? And we'll continue to talk more about how to fix these problems later. But right now, it's important just to know that this is a problem. Okay, if I go to the toolback results, I do want to mention, if I clear out this, look here, this is the same plot. So that's nice. Toolback does give us this plot. This is exactly the same as the plot that we just made. And it looks really nice too. So it's the residual, they've already labeled everything. So it's the residuals versus X. Okay? And again, you're seeing this relationship, potential relationship between the residuals and X, and you're also seeing a potential coning. Okay? So next, so we've looked at these two assumptions. Now let's consider our normality assumption. Now, if you've already failed these assumptions, testing the normality assumption is kind of pointless. But just for academic purposes right now, we'll go ahead and move forward in considering the normality assumption. But once you failed these, you have like a residual plot that looks like this. You're going to stop here and consider ways to fix this problem. Okay, but like I said, just for academic purposes, let's continue forward and think of whether or not our residuals are normally distributed. All right, so to get started with this, let's go back here and let us go ahead and just highlight our residuals. Okay, so I want to copy these ones. So press copy and then go over here, and I'm going to paste special. I want only the values, okay? So remember, on this spreadsheet, they're a formula. So when I paste them, I just want the number, okay? So that way the formula doesn't get messed up. And first thing to check this normality assumption, we could go ahead and examine a histogram of these residuals. Okay, so to get started, we can do a histogram. So go up top to insert and go ahead and highlight your residuals. So make sure they're all highlighted and press this little down button, see all charts. All charts. Go down to histogram and press OK. All right, so there's the histogram of our residuals. Histogram of residuals E. And what do we see? Does this look like it's normal distribution? No. Right? We're seeing a skewed left distribution for sure. Right? Remember the normal distribution, it would be symmetric. It would look like this. The histogram would look like a normal distribution. It would be symmetric, like that. So we're not seeing that here. Instead, we're seeing this skew, right? So we're already starting to doubt whether or not these residuals are normally distributed. But what else can we do? We can plot a probability plot. Right, and when we plot a probability plot, what we want to plot is our residuals. So we'll order our residuals first thing, and divide it by S, right? Which this is called the semi-studentized residuals. Residuals. And there are, of course, other plots that you could plot for the probability plot. But this is the one we're going to do right now. Residuals. Okay. And here, S is the square root of the mean squared error, which is basically the sum of these error terms, the residuals basically, the sum of their squares, and then divided by n minus 2. Right? So you can calculate this guy, by using these residuals. Actually, in the toolpack results, here, the standard error under summary output, this is S. So let me copy that. S, let me paste it somewhere. S equals this number. Control, it didn't get copied. Okay, Control C to copy, and Control V to paste. Okay, so the toolpack actually gives us this S value. Of course, you can calculate it yourself by, if you were to basically take each of these residuals, square each of them, continue to do that for all of them, then sum up the squares, and then divide it by, in this case, 185, since there's 187 observations, and then take the square root. You could calculate this yourself, but what you'll get is the same as the toolpack results, so we'll just use that. So first thing, let's go ahead and calculate these semi-studentized residuals. And actually, before I do that, let's order our residuals. Okay, so ordered residuals. How do we order our residuals? Highlight all your residuals. Go up top here to where it says data. Then press sort. Just continue with the current selection, it's fine. Press sort. Okay. And my data has headers, means I highlighted that label there. So that's clicked. And we're sorting it by that guy. So press OK. Okay, so now my residuals are ordered. So the semi-studentized residual equals the ordered residual divided by the 7.2, whatever. So go ahead and lock that cell, that F1 cell, using dollar signs in front of the letter and in front of the number. Press enter. Okay. Let me just format this to look a little nicer. Okay. There we go. Okay. Then get your cursor. So this has this value divided by this value, and it's the red one is locked with those dollar signs. So press enter, and then get your cursor there and then make it look like this black cross. Double click and it'll fill it all in for you. All right, so for our normal probability plot, this will be y, right? This will be the y-axis. And then for the x-axis, we usually use these ordered z-values, which are the inverse of the normal distribution of k minus 0.375 divided by n plus 0.25. Right? So I need to figure out what these ordered z-values are. Okay, I'm going to go ahead and include I'm going to include the rank number. So this was the first one, this is the second one, third one. This is basically going to be what k is. Okay, double click and it'll fill it all in for you. Okay, so z sub k, my ranked z values, are going to equal norm dot s, that's a standardized normal, dot inverse. Okay, open parentheses for that numerator, it's that rank minus 0.375. Close parentheses for the numerator, divided by, open parentheses for the denominator, 187 is our sample size, plus 0.25. Close parentheses and then close another parenthesis. Okay, press enter, and that's our ranked z-value. Double click, fill it in. All right, good. So let's see what we have here. If I were to plot these guys. So let's go to, let me move this out of the way. This histogram, I'm just going to move it down here. Okay, so I want to go to insert, and I want to do these scatter plot, move it over to the side, right click, press select data, press add, normal probability plot. My x values, okay, are going to be these z values, so go ahead and highlight. Now make sure you highlight starting with the observation. Okay, I almost did the label. So starting with the actual number, shift control down, highlight them all. Okay, scroll back up, delete that, press enter or equals, and then just semi-studentized residuals. Okay, so we have D2 to 188 and C2 to 188. Looks good. Press OK, and then press OK. And what do we see here? So, yeah, if this was a normal distribution, right? Remember, it would line up exactly on this line. Okay, and then if there was a 3, it would be, yeah, so. Right. So you're seeing this blue line, right? It doesn't look like a straight line. Instead, it's like this, right? That's kind of like that S shape. All right. So that's indicating that not only is this skewed, but it also has kind of those heavy tails. Okay. So yeah, it's not a reasonable assumption. We need to fix all of these things, starting with the fact that this model appears to potentially be misspecified, in that the heterogeneous variance assumption appears to be not working. So, at this point, making any conclusions based off of these, confidence intervals or making any inference off of these estimates, it's really not appropriate. Now, one last thing I want to talk about before I leave this conversation is that Excel, in their toolpack, they do provide this normal probability plot. All right. What is this? All right. It's kind of interesting. I really do not recommend interpreting this or using this. What they've done is they've plotted life expectancy, so our Y value, versus this sample percentile is K minus 0.5 divided by the sample size N times 100, times 100%. Right? So, so when I click on this plot, it shows me their plot. It's these two things, right? So this is the life expectancy if they sorted the life expectancy, and then this percentile. Okay, this percentile that they're plotting on the x-axis, right? It is the rank. So starting with 1, right? Because these are already sorted. It's the rank minus 0.5 divided by 187, which is our sample size, times 100%, right? So that's what they're plotting. That's what they're plotting. It doesn't really make a lot of sense for that to be a normal probability plot. So I would recommend creating that normal probability plot on your own. Of course, there are different ways to make this plot. I didn't have to use this formula here. I also didn't have to use the semi-studentized residuals. So there are other ways of making this plot. I would argue that the plot that Excel gives automatically in their data analysis tool pack, though, is somewhat misleading and just not the best normal probability plot that we have available to us.